Breaking up the algorithm of multigrid, we know what to do. Now is the question how to do it. So the part of the multigrid that we're going to need, well, we are going to need some how to jump from one mesh to the other, and then also how to perform one relaxation, as they call it here, one iteration on any mesh. So remember the notation, omega h, that's the finest mesh, omega 2h, that is a mesh with twice as big cells. So here you now have, it's a little bit cheating. So now the idea is as follows. On a fine mesh, here only 12 points, we have now an anode which is more or less smooth, low frequent. And then you make sort of a transfer from the 12 grid system down to a 6-point system and do the same representation there. So in meters, the wave is exactly the same, sort of if you look at the wavelength, but we have fewer points to describe it, so now it appears more high frequent on a coarse mesh. That's the whole point. Yeah, we don't need that one as well. Here again now the residual equation. So we are going to do the following. On the fine mesh, you do a couple of iterations, not many, 3, 4. Calculate then the anode, or actually the residual. It's fairly straightforward. And then this residual is going to turn out to be the right-hand side on the residual equation, where we are seeking now the anode. But that is going to take place on the coarse mesh system. Finding the anode, we then go back to the fine mesh solution that we had and adjust it, hopefully getting this one closer to the little u, the correct numerical solution. So that is our task. And here again, the reason why we use residual equation, we have the possibility to choose an initial solution. Then on the coarse mesh, we are seeking the new anode, and then of course we have a beautiful choice in 0 for the anode. We need something initially then to solve this residual equation here on the coarse mesh. We know the right-hand side, but we then have to start with something for the unknown, which is then the anode. Of course, we start with 0. That's the whole point. Yeah. So this then should be the recipe. If you now wanted to, say, initially solve a problem, why start on the fine mesh? Much cheaper to start on the coarse mesh. So yes, that's possible. So the first step, you do a couple of iterations on the coarse mesh system. So that is quite possible. And then take the solution, whatever you find there, and then push him upwards onto a finer and finer mesh in the end, than to have a more better initial solution on the finest mesh. So they call it here a nested iteration. Normally we will jump start on the fine mesh directly, but it's possible actually to start on the coarsest mesh. So possible, but that's not something we are going to pursue much. So here is more the algorithm now. You say you start on the fine mesh, and then you do a couple of iterations there, not many. Then we'll have a solution on the fine mesh. We will have a V super H on the fine mesh. Maybe that solution is not so good, but okay. And since we have done now a couple of iterations on the fine mesh, we have removed a lot of the high frequent noise already. So now this error that we have on the fine mesh is going to be sort of not so high frequent. Calculate the residual on the fine mesh, and then we have to transfer somehow that residual onto an equation system on a coarser mesh down here. So that R there is going to be the residual that we had, but now represented on a coarser mesh. And then we have the error which we are seeking. We guess initially 0, and then we do a couple of iterations on this equation, finding an expression for the error. And that one we can then go back, finding this error on the coarse mesh. We adjust whatever solution we had on the fine mesh to something that is hopefully more correct. So that is the sort of the two mesh multigrid. So not so multi, only two meshes, only coarse grid correction. So what we then are going to find how to do is then finding the residual on the fine mesh and how to get that residual down to a coarser mesh, and then finding the error on the coarse mesh and how to get that error back to the fine mesh, and finally then represent the original problem on a coarser mesh. The last one there, well, that's something that we may not have to worry too much about, since we are using the residual equation. But intergrid transfer, that is the key point here now. Going from one mesh to another with any signal. And as it says here, normally you will double up your mesh system. Some people has played around with a factor of square root of 2 or 1.5 or something, just to see what happens. It's actually not more efficient. So doubling up is actually quite smart. It works quite efficiently. So we are going to do it quite simple. So here now, how to transfer the error that we found on the coarse mesh, the 2H, how we can get that one onto the fine mesh. Then we are talking interpolation, or also called a prolongation. And here we are going to do it easy. We only use linear interpolation. That's definitely the most simple. The operator, intergrid transfer operator, is a large capital I. And you always read it from subscript to superscript. So it's sort of implied that you have a small arrow, no, not an arrow, an arrow pointing from sub to super. So here it's an interpolation function from the coarse mesh 2H to a fine mesh H. So this notation is widely used within multigrid, always from sub to super. So we are searching for this operator, and easier to see it graphically. So the top, there you have the coarse mesh. How to represent that signal, that error, on the fine mesh? Well, you take the points that you have already. They are just directly copied. And then you're going to need points in between. So here you just use linear interpolation. That's the simple way to do it. This is okay for this one-dimensional case. And here you have your sort of unknown in the points 0, 1, 2, 3, and so on. Now, looking at the Sola algorithm, and with the staggered mesh system, what was it like there? Here you now have a coarse mesh. One big cell, two-dimensional. You have your unknown pressure that is inside the cell. It's in the center point. How to make that one a two-dimensional case? How to make this coarse mesh into a fine mesh? So it will now look something like this. So the center point is not showing up here at all. Instead, you are going to get these 4 points here. So then you have to take this linear interpolation thing a little bit differently. So it's a question on your choice of mesh system. If you have started out something like this, and say you have a co-located mesh system, your unknowns are located here in the corners. How will this one look down here? Okay, this was one cell, now I have 4 cells. But then you see the corner points, they survive. They are just moved directly. But now you need more points. So here, linear interpolation between those two, and so on. And the midpoint, linear interpolation between all 4. Totally different way of thinking. So it depends on your initial or original mesh system. Where are your unknowns located? Just a matter of bookkeeping, of course, but using just plain linear interpolation, yeah, it can involve a little bit algebra, of course. But here, it's not a problem here. You can always take a crude representation of something and make it finer some way. Either linear interpolation, or you can use some weighting, or whatever. You can always do that. From coarse to fine, that's not any problem involved here. Rather straightforward. So the notation, you will have an operator, large I, from 2h to h. Then inserting this signal, whatever you have on the coarse mesh, into this operator. You will then be given back the fine version of the same. And for this one-dimensional case, you have the recipe here. The odd points then are just transferred directly. The even points, okay, then you have a linear calculation between them. Just take the mid value here. So that is quite okay. Here you can even construct matrices if you want to do the calculation more efficient, sort of programming efficiency, but it's not difficult. So now the problem with going the other way, that is a little bit more tricky. So going from fine mesh to coarse. Okay, look at situation A up there. All the points, both the filled and the opened, they belong now to the fine mesh solution. And on the fine mesh, I now have a smooth, nice signal. So creating a coarse mesh representation of that signal A, not a problem. You see, taking just every other point will still mimic a nice sine wave, no problem. But if your situation is like the one in B, here all the points, they are part of your fine mesh solution. And if you draw all the lines, it looks rather high frequent, going up and down, up and down and up and down. So here you have a quite complex signal on the fine mesh. If you now pick only the every second point, just the opened points, you see all of a sudden you get something smooth. That's not a good representation of the original signal. And here is the danger. If you are going to a fine mesh, to a coarse mesh, the signal that you have on the fine mesh must be smooth. You can't have any high frequent noise like the one in situation B here on the fine mesh. Here you are going from this guy straight up to him, down, up, down. No way you can give a good representation of that behavior on a coarse mesh. You have to smooth it out first. So here, this high frequent signal must be smoothed out before you can do this transfer to a coarse mesh. Clearly. Didn't he has a coarse mesh? No, he doesn't. It must be here somewhere. Two-dimensional representation from coarse to fine. Here everything is in the corner, so you do different ways of interpolation depending on which point you are looking at. So now what was tricky, from fine to coarse. A restriction, the same symbol, same operator, but now remember from sub to super. So now we go from fine mesh H to the coarse mesh 2H. And the obvious operator, you can just call it an injection. You just take every other point. That's simple injection for you. Yes, you can do that. You can also use some weighting here, saying that one point on the coarse mesh, it's sort of an average over the three locally neighboring points around the one you're interested in on the coarse mesh. So here with a weight of 1 plus 2 plus 1 is 4. So here you will then actually have a smearing effect if you use this full weighting. So normally what you do, going from fine to coarse, you only take every second point and represent it down here. Doing this full weighting, yes, it's possible, but it's a little bit dangerous. You have some sort of artificial smearing out of this original signal that you have here. Remember, this signal has to be represented as good as possible on the coarse mesh. So you shouldn't destroy it just during the intergrid transfer. Yeah. So now, if we only look at a two-mesh system, coarse grid correction scheme, we start with the fine mesh, and there we have our original equation, the algebraic equation system. Then we do new one number of iterations, or relaxations if you like, on the fine mesh. We there need an initial guess for our solution, of course. How you find that one, that's your headache, but you need to start with something. Having done a couple of iterations, you find the residual, but now you want the residual on the coarse mesh. So finding the residual on the coarse mesh, you first find it on the fine mesh here, That's the residual on the fine mesh, and then you push it through the operator, taking it from a fine mesh to a coarse mesh. Then, since we now only have a two mesh system, the equation system actually has to be solved on the coarse mesh. We could have used more mesh systems. We're coming to that later, but for now we only have two mesh systems. So yes, you need to solve the equation system somewhere, and of course you do it on the coarse mesh. It's much cheaper. So there you find a solution, a correct solution. How to find that solution? Well, that's your choice. Use a direct method, use 1 million iterations, whatever. Find a solution, a good solution on the coarse mesh. Then we know the anode here on the coarse mesh. Then we go back to the fine mesh using this anode we have just found, push him through the operator from coarse to fine mesh, and then adjust whatever we had as a solution on the fine mesh system to something that now should be much better. And then we do a couple of iterations here as well, new number 2. So these two parameters, new1 and new2, that's actually something you will find in most multi-grid algorithms. New number 1, that will be the number of iterations, number of relaxations on the way down to coarser and coarser meshes. And then on the way up again, you will use new2, number of iterations on each level. So these two parameters you'll find on most multi-grid algorithms. But here, then only two grid systems. And in practice, these parameters, new1 and new2, they don't have to be big. You don't need many iterations, 1, 2, or 3. That's good enough. Yeah. Let's try this. Here I now have an initial problem on the fine mesh system. Not that many points, as you can see. And I have now the equation system, very easy, one-dimensional, double derivative equal to 0. So I know the solution before I begin. The solution is supposed to be 0. And the initial solution I have constructed, you see, is a superposition then of several high and low frequent modes, just different sine waves added together. And it goes from -1 to +1. So this is my initial field. It's a mix of high and low frequent modes. Then we do some iterations on the fine mesh. And then we have to calculate the residual. So what you see to the right up there, it's the residual. Looking at the numbers, at the scale, it looks dangerously. What is it? 10,000, 15,000. But remember, the value itself on the residual makes no sense. So you can take the equation, multiply it with 1 million, or divide it by 1 million. You get a totally different number. So that's not the numbers there shouldn't scare you. It can still be a good approximative solution in the end. The anode doesn't have to be big, although the residual is big. Then we have to transfer the residual that we have here onto a coarser mesh. Now it's restricted. And although it's fairly high frequent up here, but still with the number of points that I've used here, this is a fairly decent representation of the numbers that we have here. Not so bad. I missed the initial point here, 10,000. He's totally gone. Never mind that. So down here now on the the coarse mesh, I now solve the equation system. I start by guessing an anode, which is 0, and I find the solution. And now I have solved it so that the equation system here is solved all the way to machine accuracy. And here it is solved using a direct method, just the Thomas algorithm, directly. So that's the solution, but only the solution on the coarse mesh system. So now we have to take the arrow that we found here. I mean, this signal here is actually the arrow. The arrow that's reported here, that's the arrow for the residual equation on the coarse mesh, so don't get confused. So this is the equation system that we have now on the coarse mesh. So I guessed initial error 0, and now the residual, that was the right hand side that was given, I know that one. Find this error precisely. Okay, I have now solved this equation perfectly. So the error actually here is 0 plus 10 to the power of minus 16 or something like that. So I have solved it as good as I can on my computer on the coarse mesh. So this is now the error on the coarse mesh. Now use that error to adjust whatever signal you had up here. Then you need to take the integrate transfer from coarse to fine and then adjust it up here. And actually you can see it. The signal down here is fairly sort of the inverse of what you have up here. So when you do it, you see you get the red solution up here. So the adjustments, very efficient. And then you continue. Do the same all over again. Now this is the signal that we now have on the fine mesh, just rescaled, so it's only 10% here. And now it's very high frequent. So we do some iterations up here to smooth it down. Here actually only one iteration. That might be a little bit too few, because then we have the residual, which now is very high frequent. Can be very hard now to represent that signal down here on the coarse mesh. So this is maybe not ideal, but let's see what happens. Solving that equation system and use that one to adjust the fine mesh. So you see that didn't work. And the reason then, it wasn't smooth enough up here when you did the integrate transfer. The coarse representation of the signal up here, that's not good. You have to smooth down your solution before you transfer it to a coarser mesh, or else the method won't work. So this is not a good idea. We need more than one on the way up and on the way down. So here new one was 1. So now let us take let's take 3. Why not? And do the same thing. That's the initial field. And then we have done 3 iterations, calculating the residual, transferring that one to a coarse mesh, solving the equation system, and then adjust whatever we had up there. Very nice indeed. So now I have this fine solution. And now I do 3 iterations on the fine mesh. That helped. Now we have a very smooth signal on the fine mesh. And this behavior very easy to represent down on the coarse mesh. Of course it is. And now finding the solution down here. Adjust. Now you see it's really efficient. So now I have a fine mesh solution which already has an error 10 to the power of minus 4. And then you can continue as long as you like. See, he's very efficient for every step. So So it's called a cycle when you go from fine to coarse and back again to fine, one cycle. So now we have the solution here after 5 cycles, 10 to the power of -7. So you see the method, oh yes, indeed, it's quite efficient. Any questions to this demonstration? I'll give you the source code so you can play around with it if you like. You have sort of the same given here in the notes here, starting with an initial field with wave number 12 plus wave number 30. Sort of that's an initial error field that we start with. And then we do 3 relaxations on each level on the way down and also on the way up again. So this is the initial field. Then after 3 iterations you get now this nice wavy line, and then we have to switch file. Then we do 3 iterations here, so the wavy motion is even damped. And then when it is after this coarse grid adjustments, you see the error is getting closer and closer to 0. Yeah, even continuing. But he only shows you here the fine mesh solution then all the time. And the problem is, of course, that on the coarse mesh you will be operating on the residual equation. It's only on the fine mesh that you have sort of a physical quantities, the real numbers that you want. So it's you can't really plot them in the same way. Here, with the 2-level system, we solve it on the coarse mesh. You solve the equation system on the coarse mesh. Now, how to solve it? Well, why use complex, expensive direct methods when we now have multigrid available? So, of course, what we do now is extend the coarse grid correction with many grid systems. So, from the coarse mesh, you go to an even coarser mesh. But then you have to sort of pay attention with the notation. The original equation system, that was A, V equals F, like that. V being our numerical approximation. On the coarse mesh, you will have A error equals the residual. And from this equation, if you are going into an even coarser mesh, so this is H, omega 2H, omega 4H, and so on. Then from this equation, you now create a new residual, but then you will have the residual of the residual. You're going to get crazy to understand what you are talking about here. So people have sort of decided we don't use this residual equation notation. On all levels, we use the same notation, although the unknown here should be the error. We write it like this anyway. And the right-hand side now is the residual from this one. And you do this notation on all grid levels. So here you have to sort of pay attention to what grid level are we on, because it will only be on the fine mesh that the unknown we are seeking actually is going to be a physical quantity, the V on the fine mesh. On the coarser mesh system, it's actually the error in the residual equation, but we still call it a V. This is just to confuse the students, of course. So now we can set up what's called a full V cycle. So we have on the finest mesh system, our equation system here. That's what we are trying to solve. And actually it shouldn't read U here, it should read V, because you can never find the real U anyway. So initially we just guess a solution, and then we do a couple of iterations up here, new 1 times. Then we find the right-hand side of the equation on the course level. That should now actually be the residual down here. But we still call him an F instead of an R. So we find the right-hand side F on level 2H by the operator from fine to coarse, where we have put in the residual. Then we do a couple of iterations on this equation. Now we are talking about this equation, which is actually the residual equation. Initial guess 0. Initial guess 0 for the unknown down there, since it is the residual equation. Smart initial guess. And so you continue coarser and coarser mesh all the way down to the coarsest mesh possible. There you solve the equation. Somewhere along the line here you need a solution. Of course you do that on the coarsest mesh. If you're lucky, you have such a coarse mesh that you are down to one single unknown, which is just solved directly. But that depends on your geometry, if that's possible, of course. Now having the solution on the coarsest mesh, then you have to nest your way back up again on finer and finer meshes. So you adjust or correct any solution that you have on one mesh system by the new solution that you find on the coarser mesh. And then on the way up again, you do also a couple of iterations. There, new number 2 pops up. That many number of iterations on each level. And then you correct and correct all the way up to the finest mesh. And then hopefully you will find a better solution up there. So that is a V cycle for you. Can be drawn like this. V cycle. Start on the fine mesh, and then you step your way to coarser and coarser mesh all the way down to the coarsest, and then go your way back up again. It's not necessarily the smartest way to do it. You might want to do a W cycle or something like this, going a little bit in between the coarser and finer mesh on the way before you finally go back to the finest mesh. So what is clever here, that's not necessarily so easy to know. You have a numerical theory. You can do a lot of calculations finding out when you are standing on one grid level, what's the smart move? Where should I go from here? Should I stay on this level and do some more iterations? Should I go to coarser mesh? Should I go to finer mesh? Maybe I should skip one mesh level and jump directly from 4H to 16H, something like that should also be possible. And yes, it's possible to find the optimum road, you might say, through this different mesh systems. But then you are going to spend more CPU hours deciding how to do it and actually to solve the problem. So for an engineer, forget it. You say V cycles, and then you do as many V cycles as necessary until you have a good enough solution. Do it simple. If you are interested in numerical math, okay, then that's a different topic. Then you can play around with problems like this, finding the optimum road. So the last one here, that's sort of a suggestion then for a full multigrid V cycle, saying that initially I don't even have a good guess for my solution on the fine level. Hence you start on the coarsest level. You start down there, very easy to find a solution there, and then you try to push this solution up to finer and finer mesh, and you do it like this before you are here finally first time on the fine mesh level. And then you should have a very good initial start for your unknowns. That can be a very smart way to start the process. And from here on, you will now continue with full V cycles. So, yeah, you have some possible programming tricks here. Program it recursively. We don't have to look into the details here. So instead, let us look at a demonstration. Here, I have now set 3 iterations on the way down, 2 iterations on the way up again. Weighted weighted Gauss-Seidel, omega is 2/3. And we have sort of the same problem. I create an initial field here with little random, little noise. So we have typically here some low frequent modes in the anode and also some high frequent. So then some iterations on the fine level. Remember, it has to be smooth before you are capable of transporting that one to a coarser mesh system. So to the right, I now have the residual on the fine mesh. Now push that one down to a coarser mesh. That's a decent representation of the signal, isn't it? Not that bad, at least. Then we do a couple of iterations on this level. Initial anode, 0. Initial guess is 0. But now we find a solution here after 3 iterations. And if you compare to what it is above, you see fairly close to the inverse of what you have up here. So adding these two together should be good. But we can make this solution better. It's only 3 iterations. So then we continue, finding now the new residual on the level 2. That's that one. Transfer it down to an even coarser mesh. And so we continue. Finding the field down there. Finding the new residual. Move it to an even coarser mesh. Solving or iterating 3 times there. New residual. And then finally I'm left to one single point, which then is of course solved directly. So now I'm all the way down on the coarsest mesh. Now we have to nest our way back up again. And then it's a good way to ask, what's the memory requirement here? What do you need to store in this method? You never store the coefficient matrix. That's just some numbers which are fairly easy to find whenever you need them. So you don't store the entire A matrix. That would be silly. But here you need 1 vector for all your unknowns and then 1 vector for the right hand side on the fine mesh. So we are going to need V, H, and the right hand side H. On the coarse mesh you're going to need exactly the same, but they will be only half as big. But you need both sides, and you need to store them, because when you are going down into even coarser meshes and then finally trying to go back up again, you still need the full equation system here. We are going to adjust this one and then do a couple of more iterations, so we still need to remember the right hand side on all levels. So both left and right hand side of the equation system, that's what we need storage for. But of course in 2 dimension, and not to mention 3 dimension, the coarse level memory requirements are so small that you don't even bother about it. So it's a very economic algorithm when it comes to storage. Okay, back here we have the solution, correct solution on the coarsest mesh. So now we are taking this solution here and adjust whatever we had up here. So that's the adjustment. Didn't adjust so much, but a little bit. And then, and remember, here it's impossible to look at the physics in the problem, because you have the residual equation of the residual equation of the residual equation many times. So it doesn't make sense physically. Also look at the numbers, just forget to try to understand what they mean. That's not the point. It's only on the fine level that we can actually understand what's going on. So here, 2 iterations now, finding the new residual, solving that equation system, and adjust on level 3, and so we continue all the way up. The adjustment is not that big, a little bit. Some iterations there, finding the new residual there. Not that we need the right-hand side now, but and there finally you see the adjustments on the fine level. Now we are talking the real numbers, and you see quite efficient. So he has reduced the error a lot, and now our new system should be, our new solution should be much closer to the correct answer. And then you can do it all over again. Telescoping your way down, and then solve it, and then adjust on the way up again. And then the adjustments there. Not that efficient this time, but still not so stupid. Let's take another V cycle, and so on. That was 3 V cycles. Any questions to that one? Then we take a break.